right, so we took care of one example. Let's take a look at another one where we're actually going to need this slope formula that I have conveniently left on the board from the previous video. So we're asked to find the slope of the line. So between, make sure I get my points right. So I have 6, -5. And then I have 4, 2. So again, remember, these are x, y pairs. So the guys that come second are going to be the ones on the top of the slope formula. So m equals, and technically you might worry about which one's x1, y1, which one's x2, y2. It really doesn't matter so long as you keep things lined up appropriately. So I'm going to list the 2 in that instance. And then that means that the 4 needs to be underneath it in the formula. So I have 2 minus this other y coordinate of -5. And then down below I have 4 minus 6. All right, so now if I work out the arithmetic here, 2 minus -5, that's 2 plus 5, so that's 7. 4 minus 6 would be -2. I would normally write this as -7/2 for my slope. If you wanted a decimal, -3.5 is fine, but I really do tend to try to keep slopes as like reduced fractions if I can, so I don't have to worry about rounding or anything. All right, so now suppose we got a slope. This isn't actually in the notes file, but I'm just kind of working on it from here. Say we wanted an equation for the line between these 2 points. So what I'm going to do, I'm going to use the point slope form to get an equation for the line, because this is something that we have to do from time to time. So now I've got my slope m, and then I pick a point. Doesn't really matter which one in this case. So I'll go y minus, I'll just use this one. So y minus a -5, well, that's y plus 5. So again, remember, minuses are baked into the point slope formula. Equals -7/2 times x minus my x coordinate. So I'd have -7/2 times x minus 6. You could have just as readily used the 2 and the 4, and I may end up regretting that I didn't, but I have already, so there we go. Now, that's the point slope form. That's a perfectly valid equation. You end up getting an also perfectly valid equation if you use the other points. This is where that slope-intercept form comes in handy, because as it turns out, the line's only going to have one y-intercept. So this and what happens with if you use the 2 and the 4 instead, it better straighten out to give us the same thing. It will. So if we wanted the slope-intercept, it's not really all that challenging. We basically just need to kind of rearrange things so that y is by itself. If you go back and look at the formula, for the slope-intercept, it's just y equals mx plus b. So we'll need to kind of distribute that -7/2 to clean it up, but the real effort is just making sure that y is by itself. So we have y equals, I'm going to go ahead and distribute the -7/2. So we have -7/2x plus 7, -7/2 times -6. That's going to end up giving me a plus 21, I believe. So you have positive 42 over 2. All right. So then I needed to subtract over that 5, right? Okay. So we have y equals -7/2x plus 16. All right. So that's that done. All right. So we've got the line's equation, a point slope form. We could produce another one. We could produce a whole bunch of them if we had a whole bunch of points on the line. Or the slope intercept, which as it turns out is in fact unique. So that's kind of handy. All right. So now we're still going to end up, we don't really need the slope formula for this next example. It's actually kind of given to us in a sense because of the fact that we already have an equation for the line. So let's take a look at this next example. All right, so we're given the equation 2x minus 3y equals 18. Okay, so we're asked to find the slope, the y-intercept, and then sketch a graph. I'm going to be honest, I'm going to kind of punt on the graph sketching part of this because I think, you'll see why. We're eventually going to use some, computer tools to do graphing for us, but you should be able to pull out x and y intercepts and plot points just fine on this thing if you want to do it by hand. But anyway, so to get the slope and the y-intercept, I'm going to take this and I want to get the equation in the same kind of slope-intercept form that we did right here. So once again, I just need to get y by itself. So what do I need to do to get y by itself? Well, I got to subtract over the 2x. So we have negative 3y equals, I would normally write that as 18 minus 2x. I like to lead with positive terms, but to make it look like the mx plus b, I think it's better to go this way. And so now what's left for me to do to get y by itself? That's right, I got to divide by negative 3. So we have y by itself on the left-hand side. On the right, we have this whole thing over 3, which I guess is okay, but you can actually break the fraction up, and you would get positive 2/3 x minus 18 divided by 3, basically just dividing each term by 3 separately, and 18 divided by negative 3 gives us negative 6. Okay, so we've got the slope-intercept form. And what's really cool about the slope-intercept form is the stuff we're asked for, we can just rip straight out of this thing. Because the slope is the coefficient of x. The y-intercept is that constant hovering around in the back. Well, the y-coordinate of the y-intercept. The x-coordinate's always 0. So our slope is going to be 2/3, and the y-intercept, as I said, I'm usually okay with y equals negative 6 if you write it out on a paper test, but WebAssign will often ask for like an x-y coordinate pair, so I'm going to write it as 0, negative 6. As I said, you can sketch a graph from here. It's actually, it might not be a bad exercise of sort of using that rise over run thing. So plot the y-intercept and then move over 3 units in the x direction, climb up 2 units in the y direction, plot a point, and then connect the dots. You can do it that way if you'd like. All right. So now the last few examples, well, one kind of deals with an application, but the next 2 examples come back to that notion of lines being perpendicular and parallel. So normally I kind of get, the definitions as we have them on that front page kind of bother me, because technically parallel lines are lines in the same plane that never touch each other. They never intersect. But as it turns out, if you've got equations for the lines and you can get hold of their slopes, it turns out that matches up with the slopes being equal to each other. Again, I flipped back to the first page of the notes if you want to look at those definitions. Perpendicular lines, they cross at like right angles. So, like that. So you get the little square right there. But as it turns out, there's a similar linkage with slope. It's just not as straightforward as them being the same. There's this thing where it's kind of like a double inverse. It's a negative reciprocal. So if you have one slope, you flip it over and then apply a negative to whatever it is. So negative will become positive and vice versa. So if the slopes are the same, the lines are parallel. If the slopes are this negative reciprocal thing, they're perpendicular. If neither of those 2 things happen, they're neither parallel nor perpendicular. Hopefully that's straightforward enough. All right, so we're given a couple of lines here at the bottom of this, this second page, example 4, if you're following along with the numbers. And it says we're given a couple of equations and we want to figure out whether they're parallel, perpendicular, or neither. So our equations look like this. So we have 8x plus 5y is 2, and then we have 5x minus 8y equals 3. All right, and believe it or not, we're going to do the exact same thing we did here to figure out what's going on. Let's go look at the slopes, which means let's rearrange these equations into that slope-intercept form. I subtract over my 8x, 5y equals negative 8x plus 2, then divide by 5, y equals negative 8/5 x plus 2/5. If you've written the whole thing over 5 first, that's fine. So our slope for this first line is negative 8/5. What about this guy? Well, we subtract over the 5x, so we have negative 8y equals negative 5x plus 3. Now we need to divide by negative 8. Well, we divide by negative 8. Negative 5 divided by negative 8. 2 negatives. The negatives, bash into each other like the Monday Night Football helmets and go poof. We have positive 5/8 minus 3/8. So as it turns out, we don't really need these constant terms. The y-intercepts don't mean anything to us as far as parallel or perpendicular. We just need to zero in on these slopes. Are they exactly the same? No, they're not. So they're not parallel. Are they negative reciprocals? Well, if we take this and we flip it over, we'd have negative 5/8, and then when we take the negative goes bye-bye. So they are, in fact, negative reciprocals. So we have negative reciprocal slopes in this instance. So they're perpendicular. All right. So I've got a couple more examples I want to take a look at. One of them is going to visit this parallel perpendicular thing again, and then I mentioned there's an application kind of thing bringing this section home. So I'm short on time to get them both in at once. So rather than just ending up with one video that's like 3 minutes of me talking about one example, we'll pick up with this next time.